Chemistry, we're moving on to lesson 10 in the foundations unit. This is on constructing an atom. So first we're going to learn to read the four main components of a periodic table. So the first is called the atomic number. This is the number of protons that an element has. It's the number of protons that gives an identity to the element. So it's not the number of neutrons or the number of electrons. That can be different. But as long as an element has a particular number of protons, it remains to be that element. So hydrogen, for example, must have one proton. The atomic number is also the number of electrons that an element has in its electrically neutral state. So when an element is born, it has to have an equal number of positive and negative charges. So if a hydrogen atom in its natural state has one proton, it will also have one electron. Electrically neutral means that the number of protons and electrons are the same. The atomic number is also called the Z number. We tend not to use that term a lot, but you will see that term Z number. The atomic symbol. This is the abbreviation for the element used in chemical equations. Atomic symbols are often based on Greek or Latin names, so the letters don't always seem to match the element name. The atomic symbols are international. No matter what language the scientist speaks, the symbol for hydrogen is always going to be an H. So even scientists in, say, Germany or China or Mexico, they're all going to use H for hydrogen, no matter what the name of hydrogen is in their local language. The atomic name, this is the name of the element. Atomic names can vary by language. However, the atomic symbols are universal across languages. The atomic mass. This is the average of the masses of all isotopes of an element. The atomic mass is the average mass of all isotopes for an element. This accounts for the decimal number value. So for example, let's just take a simple example. If 50% of the isotopes of a particular element have a mass of 3 and 50% have a mass of 4, then the atomic mass of that element would be 3.5. So the mass numbers of a particular isotope are whole numbers. But the atomic mass, which is the average of all of the mass numbers of all the different isotopes of that element, can be a decimal because it is an average. So the rows in the periodic table are called periods, and the columns are called groups. Generally in this class, we'll tend to call them rows and columns. That's a little more natural to do that, but if you hear period, it means a row. If you hear if you hear period, it means a row. If you hear group, it means a column. So each period represents a new orbital. So the first orbital is represented by the first two elements. Now, let's think about what's happening there. Hydrogen has an atomic number of 1, and the whole periodic table is ordered in the order of atomic numbers. So hydrogen has an atomic number of 1, and helium over on the right side has an atomic number of 2. That means hydrogen in its natural state has 1 electron, helium has 2 electrons, and both of those electrons for helium are in the first orbital. So once you're at the end of a row, you're at the end of that orbital. No more electrons will go into that orbital. So the first orbital can hold 2 electrons. Now when we go down to the second row, that's the elements lithium, Li, all the way through neon, Ne, over on the right. Each one of those adds an electron. So lithium, first of all of those elements have 2 orbitals because they're in the second row. So lithium has 2 electrons in its first orbital and 1 electron in its second orbital. When you move to beryllium, Be, it has 2 electrons in its first orbital and 2 electrons in its second orbital. So it has an atomic number of 4. So 2 of the electrons are in the first orbital, 2 are in the second orbital. As we go across, all of the elements in the second row have 2 electrons in the first orbital. So if you move over to boron, it has a total of 5 electrons, 2 in the first and 3 in the second. Carbon has 2 in the first and 4 in the second. Nitrogen, N, has 2 in the first and 5 in the second. Oxygen has 2 in the first and 6 in the second. Fluorine, F, 2 in the first and 7 in the second. And finally, neon at the end of the row has 2 in the first and 8 electrons in the second orbital. So the second orbital can hold 8 electrons, and then it's full. And then you go down to the third row, and that's going to be the third orbital. And the same progression occurs there. For sodium, which is Na, it has 2 electrons in the first orbital, 8 in the second, and then it has 1 in the first. Magnesium, 2 in the first, 8 in the second, 2 in the third. And so it goes across there. So the next, as you go down, K, potassium, and everything in that row is the fourth orbital. Actually, almost true. We'll talk about the specifics of that in a little bit later. The fifth row is the fifth orbital, the sixth row is the sixth orbital, and so on. So each group, that's each column, represents an additional valence electron. So valence electrons. So hydrogen in the first column has 1 valence electron. That is 1 electron in its outer orbital, which is its first orbital. If you go down to the next row, that's lithium, Li, its valence orbital is the second orbital, and it has 1 electron in its second orbital. We just said that. It has 2 in the first and 1 in the second. If you go down to sodium, Na, the third orbital, sodium has 2 in the first, 8 in the second. It has a full second orbital, and then it has 1 valence electron, 1 electron in its outer orbital, which is its third orbital. Next, you go down to K, potassium. It has a full first orbital, 2 electrons, a full second orbital, 8 electrons, a full third orbital, 8 electrons, and then it has 1 electron in its valence orbital. That would be its outer orbital, its fourth orbital. So everything in the first column has 1 electron in its outermost orbital. The next column over would be 2 electrons. That's everything from beryllium, magnesium, calcium, strontium, Sr on the way down. Those have 2 electrons in their outermost orbital. Now you jump across. These are all what are called the A group elements or representative elements. And you notice we jumped over now across the transition metals. Transition metals do not contribute valence electrons. So boron in the second orbital has 2 orbitals, and it has 3 electrons in its second orbital. Carbon is 4, nitrogen is 5, oxygen is 6, fluorine is 7, and neon is 8. And then as you go down to the third row, you go from sodium across to Ar, argon, and you can see the number of electrons. It would have the same number of electrons, it's just the outer orbital of the third row is the third orbital. So you continue on down from there. Again, only those light blue elements, the transition metals, do not contribute valence electrons. Again, the key to valence electrons is that they are the outermost electrons. Those are the ones that do the chemical bonding, and that's what allows different elements to be put together into different compounds and different substances. Okay, so now we're going to build an atom. It's not important that you memorize the periodic table, but you should understand how to read it. And a good exercise for doing that is diagramming an atom. So this is kind of a standard format that I have for diagramming atoms. So I picked silicon. It's in the third row. And there you see kind of a condensed version of the periodic table there. You'll notice I closed that gap where the transition metals are. So for example, in the second row, you go from lithium to beryllium, and then you have that big gap over to boron if you look at your periodic table. I just went ahead and closed that up. We're not going to deal with the transition metals here. So we're going to just jump from beryllium straight over to boron and so on. Okay, so how do you diagram this atom? Well, one thing I have students do is you diagram or you write out what I call the scoreboard. And you're going to keep track of how many protons, how many electrons, how many neutrons, how many orbitals, and finally, how many electrons in the valence or outer orbital, because that's where the action is. That's where the electrons are bonding and connecting with the electrons in other atoms to form chemical bonds. Down there in the middle, that big open area, we're going to draw the diagram of the silicon atom. There you see the nucleus. It has some number of protons and some number of neutrons, which we're going to determine here in just a second. I draw the nucleus as a rectangle rather than a circle because I don't want it to get confused with the orbitals. Okay, so let's go ahead and do that. So step one. So silicon has an atomic number of 14. That's the number. You see the symbol from the periodic table, or the box from the periodic table up in the upper left corner there. So silicon has an atomic number of 14. So that means it has 14 protons, and in its natural electrically neutral state, it also has 14 electrons. 14 protons, 14 electrons. So we'll go ahead and fill in the scoreboard right there. And that's the protons, and then the electrons go right there. And now we can also fill in the nucleus. Rather than draw 14 circles with plus signs, which would represent protons, that's too many. So let's just put the number 14 there in the nucleus down there in the center box there. Okay? So now we're ready to move on to neutrons. And we're first going to put the electrons, the 14 electrons, we're going to put them off to the side. We're going to place those at the very end. Okay, but those are 14 electrons off to the side. Now we'll move on to neutrons. So now we round the atomic mass to the nearest whole number. This will be the most common isotope of silicon, which is Si28. So remember, that atomic number 28.09 is an average of different isotopes of silicon. So for example, silicon mostly has a mass number of 28. 28 protons, 28 neutrons. Remember that each proton and each neutron has a mass of 1 atomic mass unit. So if you know the mass number of that particular element, then you know how many total protons and neutrons it has, because each one has a mass of 1. So let's say, for example, I had an element with a mass number of 11. That means since each proton and each neutron has a mass of 1, then that means it must have a total of 11 protons and neutrons. You may not know how many are protons and how many are neutrons, but there's a total of 11. Now you might ask, well, what about the electrons? Don't they have mass? They do, but in these calculations we ignore the mass of the electrons because it's so small. Okay, so we're going to say that the most common isotope of silicon in this case is silicon-28, because 28.9 means that most of the silicon atoms have a mass number of 28. A very small number might have a mass number of 29, and even a tiny, tiny fraction might have a mass number of 30. And when you average all those together, you end up with that number of 28.09. So we're just going to say that the most common isotope is just going to be 28. It's got to be a whole number. So that number right there, watch what happens to it. We're going to just round it down, round it down to 28. Okay, let's keep on going. So now we're going to calculate the number of neutrons. So now we can calculate the number of neutrons by subtracting the atomic number from the mass number. So the mass number, since each proton and each neutron has a mass of 1 atomic mass unit, if I know that the mass of this isotope of silicon is 28, then it must have a total of 28 protons plus neutrons. So we're going to put that number right there in that green box. Now we're going to subtract the atomic number. Why? Because we know that's the number of protons. That's 14. So we know that it has 28 protons plus neutrons, and 14 of them are protons. So if we just do a simple subtraction there, we can calculate how many are neutrons. And that's this number down on the bottom, and that number is going to be 14. So it has 28 nucleons, that's protons and neutrons. Each one has a mass of 1 atomic mass unit, so that means the atomic mass, or the mass number rather, is 28. So it has 28 protons and neutrons. We know that 14 of them are protons, so that means the other 14 have to be neutrons. So now we can continue to fill in our scoreboard over there where it says neutrons, and we can fill in the nucleus of our atom 14. So now we're done with the nucleus. We would have, if I drew those out, we would have 14 little circles with plus signs and 14 little circles with equal signs representing the neutrons, but that's too much, so we're just going to write protons 14, neutrons 14. So now we're gonna count how many orbitals silicon has. So because silicon is in the third period row, it has 3 orbitals. So everything that you see being covered over in green has 3 orbitals. Everything from sodium Na all the way across to argon Ar on the right, those all have 3 orbitals because they're all in the third row. So here we go. We're going to draw them. Remember, this is not just counting numbers. We're going to actually diagram this atom. So first we'll put the scoreboard. You see orbitals got filled in on the scoreboard there at 3. So here they come. And there's 1. There's the second orbital. And there's the third orbital. Okay, so silicon has 3 orbitals. All right, now we're ready to place our electrons. Before we actually count the electrons in the valence orbital, we could do that right now. We're going to go ahead and just place the electrons. And I'm going to show you a particular order or way that I want you to do that. So we're going to go ahead and start placing electrons. So the first ones are going to go in the first orbital. So now we place the electrons. The first orbital gets 2 electrons, then it's full. The second orbital gets 8 electrons, then it's full. And the final 4 electrons go in the outer orbital, that's the valence orbital, and they're spread out. Okay, so let's watch this. So there's the first electron, and there's the second electron. And now we filled up the first orbital, because the first orbital, represented by hydrogen and helium, can only hold 2 electrons because it only has 2 elements in the first row, hydrogen and helium. So now that first orbital is filled. So we'll put a no vacancy sign there. We can't fit any more electrons in the first orbital. So now we go down to the second row that starts with lithium, Li, and we start placing the electrons. And I want you to watch how I place them. The first one goes there. Now the second one is not going to go right next to it. Think about when you go into an empty movie theater to watch a movie. You sit down. Somebody else comes in. They sit down, but they don't sit right next to you. They don't know you and you don't know them, so they sit apart from you a little bit. Then the next person comes in and they sit apart from both of you. And then everybody who comes in sits apart from everyone else. And then when the theater starts to get crowded, then people have to start sitting next to each other. So watch what happens here as we place the 8 electrons that go in the second orbital. We put the first one there. Now why the bottom? No reason. It could have been anywhere, but I usually just start on the bottom. Now the second one is going to go over here. It's going to spread out from that first electron in the second orbital, so they're spacing themselves out. Now we're going to go to the third electron, and we're going to put that up here. Now the fourth electron, we're going to put that right here. Now we have 4 electrons. And this has a name for it, but we won't get into that name right now. We'll learn it later as to why electrons space themselves out like this. But now it's starting to get crowded in there, so electrons are going to have to start pairing up. So the 5th electron is going to go down next to the first one, so it pairs up there. The 6th electron goes over there. The 7th there. And the 8th goes right there. So you end up with a filled second orbital. And so since you have 3 orbitals, you know you had to fill up the first and the second. Otherwise, you wouldn't have a third orbital with electrons. So we're done with those 2. So now there's a no vacancy sign there. You can't fit any more electrons in the second orbital. Again, the second row has 8 elements in it. So therefore, that orbital, second orbital, can only hold 8 electrons. Now we're ready to fill in the third orbital. So the first electron comes down here. And then they're going to space out just the way like they did in the second orbital. Third one goes up there. Fourth one goes over here. And now we're out of electrons. We've placed all of our electrons. So we know that silicon, we see that it has 4 valence electrons. Remember, those are the electrons in the outermost orbital. Those are the valence electrons. Again, valence means outer electrons, outer orbital. So we know that silicon has 4 valence electrons because this is the 4th element in its row. So watch, we'll just count. We could have known that by just counting. So there's the first valence electron, that's sodium, then magnesium, and then aluminum, and finally the 4th element over in the 3rd row is silicon, so that means it has 4 valence electrons. And so now we can fill in the scoreboard down there at the bottom, and there it comes. And now we've completed everything. We filled in our scoreboard and we've diagrammed our atom. And so that takes care of silicon. So that's how you diagram it. So this is a good exercise to understand how the periodic table is constructed, what the rows mean, what the columns mean. So I'll have you do a number of these to get used to that concept. And they're not very hard. They just take a little practice of doing them a few times and you'll understand them. All right, and that takes care of this lesson on how to construct an atom. Again, it's not important to memorize the periodic table, but you should know how to read the periodic table and understand what the rows and columns mean and how that contributes to the structure of an atom.